Hello class, this is Mr. McAllen, and today I'm going to do something different. I'm going to give you a video lesson for lesson 3.3, and this lesson will be to demonstrate the shortcuts for derivatives for polynomial functions. So we're going to first go over the shortcuts, then we're going to talk about how you use your shortcuts to find equations of tangent and normal lines quicker, and then I'm going to give you the shortcut rule if you have a product or a quotient of two functions. So anyway, let's get started with this. Let's talk about our first most basic function. Let's say your function is a constant, f of x equals c. Another way to write this function would be f of x equals the constant times x to the 0 power, because we know that a 0 power forces this value to equal 1, so that would then appear to be just plain old constant. We should know that the slope of a constant line, let's say it was f of x is equal to 8, or, well, on this grid, let's just say it's equal to 2, so I can graph it, would just be horizontal, and we should know that the slope of that line, which is also the derivative, is equal to 0. So there should be no confusion to the fact that if you have a function that is a constant line, it's not changing at all, and therefore the derivative of that function, or of that constant, is equal to 0. We're going to come back and prove this in a second. The next type of function is the function, let's call it just a linear function, x to the first power. And when we did everybody should know that the slope of this function is equal to 1, because the coefficient in front is equal to 1. So the derivative for the function x is always equal to 1. And we can show that with a difference quotient. So I'll just do the limit as x goes to a of f of x minus f of a all over x minus a. I'll just show that the long way. This is f of x is x, and f of a is a, and I'm going to put that over x minus a. So hopefully it's not hard to understand that this limit is equal to 1. So the derivative of plain old x is equal to 1. Let's do one more. We'll do the quadratic, and I'll say f of x equal to x squared. So if we do the limit as x approaches a of f of x minus f of a all over x minus a, we see that you have x squared minus a squared all over x minus a. And when we simplify the limit, hopefully you see that, as we did in class many times, that the limit is equal to 2a, and that would be, or if you want to consider it in terms of the function x, the derivative at x equals a of x squared is equal to 2a. So we see there's like there's a pattern going on here hopefully you see there's a pattern going on here with the exponents. And if you haven't seen the pattern yet, all the physics kids can tell you about it. But the pattern is basically called the power rule. And the power rule can only be used on power functions. And it basically works like this. If you have a function, let's call it b is a constant, and you have x to the n, and you want to find its derivative, then you bring the power down in front, you leave the coefficient alone because it's a multiple, and you reduce the power by 1. So when we were doing the derivative before of x to the second power, that equaled, you bring the 2 down in front, multiply by x, reduce the power by 1. So we end up getting a formula of 2x. When we had a function, when it was a linear function, what we did was we brought the 1 down in front, we reduced the power by 1, and we end up getting a constant value of 1. And when we had the very first one we did, where we found the derivative was equal to 0, if you take the derivative of a number, let's say the number is 4, remember it has x to the 0 power. It's a constant function, has a polynomial order of x to the 0. So when we apply the product rule, I'm sorry, not the product rule, the power rule, you bring the 0 down in front, multiply it by 4, you reduce the power by 1, but that doesn't matter because 0 times anything is 0. So that shows us that the slope of any constant function is going to be 0. And that's something we know from pre-calculus anyway. So now let's try what happens if we have a power function of this form, where we have f of x is equal to 1 over x squared. Well, this can be rewritten in power form. And we can use derivative notation and take advantage of the power form and bring the negative 2 down in front. X would then be raised to 1 less the power it was before. Now this is a big mistake people make. They always want to make this power negative 1, but it's actually negative 3, because a reduction of 1 brings the power down to the negative third power, and this would appropriately be written as 2 over x cubed. So that would be the derivative of 1 over x squared. Now, how do we use this in some of our problems? Instead of having to do the difference quotient all the time, let's just say we have an example, and to save you the time of hearing me talk, I'm just going to write it up and I'll resume the video. Okay, so here's a problem. Suppose that a position function is equal to negative 16t squared plus 10t plus 5. And we want to just find the derivative of that without having to use the difference quotient. We want to use a shortcut. So what we'll do is first make sure that it's a power function. Each of 3 parts is a power function, and we'll take the derivative of each term, term by term. So I'll take the derivative of negative 16t squared, and I'll add to it the derivative of 10t, and I'll add to it the derivative of 5. Because the terms are being added or subtracted, we can take individual derivatives of each term and then add them all together. So the shortcut rule for the first part would be bring the 2 down in front, multiply by negative 16, and reduce the power by 1. On the next one, we would bring the 1 down from the power of t. That would come down in front of 10, and then we would have t to the 0 power. And that would just be a constant of 1. And the last part, the derivative of any constant number, like we learned before, is equal to 0. So we would then just simplify this, and we'd have negative 32t plus 10. And that would be our derivative of position with respect to time. You can go ahead and take another derivative. If you want to take the second derivative of position with respect to time, the notation would be as follows. And that would be by doing the power rule again. So we'll take the derivative with respect to time of negative 32t plus the derivative with respect to time of 10. And what we get is, in result, is negative 32 times 1, because that's the power coming down the front, times t to the 0, which will just be constant, plus a 0, because once again, the derivative of a constant is equal to 0. So our final answer here is going to be negative 32 for the second derivative of position. Moving along, let's figure out how we're going to use this to help us do a equation of horizontal tangency. So we'll look at a problem. We'll say, let's say that we have, does this curve y equals x to the fourth minus 2x squared plus 2 have any x coordinates with horizontal tangency. Well, what we need to do is, for horizontal tangency, remember that we could have a wild and crazy curve, but we need to find out where the derivative would equal 0. So our approach is take the derivative, remember to do term by term, rewrite it, and now you have the derivative that we want to set equal to 0. We want to set it equal to 0 because when you have horizontal tangency, the slope is equal to 0. So I'm going to set that equal to 0, factor out a 4 and an x, and I have x squared minus minus 1, and I could set each term equal to 0. So I have x is equal to 0 and x squared minus 1 is equal to 0. I would say I have one location and I need to factor this one. So I have x plus 1, x minus 1, and I have 3 locations where I have horizontal tangency. So horizontal tangency can be found at x equals 0, x equals negative 1, x equals 1, because at these locations the derivative of the function y is equal to 0. Now here's one for you to try. Find the coordinates of points of horizontal tangency for the function f of x equals x cubed minus x. Hello class, I have again one more example, because I promised you at the beginning with my objectives that we would go over how to find equations of horizontal and tangent lines and normal lines. So I have an example here of a polynomial where we're going to find the equation of a tangent line at a specific point without using the difference quotient. So the first thing you need to do is you need, for an equation of a line, you need a point and the slope. So I'm just writing up the general formula, and we need to fill in the x value, the y value, and the slope value. So we're going to get we have the x value from x equals 1. We're going to find the y value from plugging it into the equation. So we're going to have 1 over 3 plus 1 over 2 plus 1, which will be equal to, I'm just going to do my work with my fractions, and my y value will be 5 1 and 5/6, or I could say 11 over 6. So I'm going to have y minus 11 over 6 equals my slope value times x minus 1. And now I'm going to use my derivative. So this is where I use my shortcut and save a lot of time. My derivative with respect to x is equal to 3x squared over 3. Remember, the 3 came down in front and I reduced the power by 1. Plus the next one, I'm going to bring the 2 down. It'll be 2x the first power over 2 plus 1. And notice how in this problem it's so nicely designed that the 3's cancel, I have x squared, the 2's cancel, I have x, and 1. So now all I need to do is evaluate the derivative at x equals 1. And do you like that? That's called the evaluation bar. So that means that I'm going to evaluate the derivative at x equals 1, and then I can plug in 1 squared plus 1 plus 1, and this is going to equal a slope of 3. So now I rewrite my equation. I'll just bring it on down here. Y minus 11 over 6 equals 3 times x minus 1. And this would be sufficient for an equation of a tangent line. And hopefully you know what to do if we want an equation of a normal line. So that's all I have for you today. Remember the power rule, just to recap. The power rule says that if you have a function that is a polynomial with a power, it has to be a power function. So if it is of the form where it's a times x to the n, where a is a constant, then the derivative will be, bring the n down in front, you have a as a multiple times x to the reduce the power by 1. Also, you can apply this rule to functions that look like hyperbolas. For instance, y equals 1 over x. It can be applied to that because that can be rewritten as y equals x to the negative first power. And when you do that derivative, remember to reduce the power. You have negative 1 you bring down in front, x to the negative second. So remember, that is the reduction of power. I hope this video helped, and again, I look forward to hearing your feedback tomorrow as far as what you got out of this video, and I hope this moves us along quicker during the year. Take care and see you tomorrow. Goodbye.